Okay, so we're continuing on with our equilibrium exam questions. Here we have the 2018 paper, and this chapter came up in question 9, so it's a whole question, and we know that each question is worth 50 marks. So the first thing that we're asked is what is meant by chemical equilibrium? So this is basically asking us for our chemical equilibrium definition that you should all know by now, and if you don't, you know yourselves, you just need to go away and learn that. Okay, part B, we're asked to write the equilibrium constant, so the Kc for the reaction. So we know that when we're writing the Kc, we're using these square brackets to indicate concentration in moles per liter at equilibrium. We have our products over our reactants, and they are raised to the power of the coefficient from the equation for the reaction. So I've got my two reactants here, CO and Cl2, and they are both raised to the power of 1 because that is their coefficient in the equation. Okay, so that's part B. Let's have a look at part C. So we're told that under certain conditions in a closed container, the equilibrium mixture is green. So what I'm actually going to do is write this out here nice and big so that we can talk about it. So we've got CO, Cl2, COCl2. We know that this is green, and we know that this is colorless. Okay. So, the first thing that they tell us is that under specific conditions, the mixture is green. Now that means that because our reactant is green, that means in terms of our equilibrium that the reverse reaction is being favored, and we have more of that green product than we have of our green reactant than we have of our colorless product. So now they're going to give us a few different conditions and ask us how that is going to affect our equilibrium mixture. So the first thing that we're asked is what's going to happen to the color if we were to increase the pressure by reducing the size of the container. So I'm just going to get a different color here. So when we're looking at the pressure, the first thing we want to ask ourselves is, first of all, is it a gaseous reaction? And looking at these little G symbols in our question, yes, indeed, it is a gaseous reaction. So we know that pressure can have an effect on where the equilibrium lies in this system. The next thing we need to be looking at is the number of molecules on each side, because we know that by Le Chatelier's principle, if we were to increase the pressure, the reaction that produces the smallest number of molecules is going to be favored. So we know on this reactant side, we've got 2 molecules. On this product side, we've only got 1 molecule. Now, what does that mean for an increase in pressure? Well, that means that our forward reaction is going to be favored. Now, what is that going to do to the color? Now, we would automatically look at these colors and say, oh, well, if the forward reaction is favored, then it's going to go colorless. But in fact, if it goes completely colorless, then that means that the reaction has gone to completion and we have no reactant there at all. Now, that's not how the equilibrium works. We can, of course, force it to go to completion, but more often than not, what's going to happen is we're still going to have some of that reverse reaction happening. So rather than the mixture going completely colorless, the color is going to fade. Spell correctly. So the green color is going to fade. Can't spell color today, guys. So as we increase the pressure, the forward reaction is favored because it is the reaction that produces the smallest number of molecules, and therefore the green color is going to fade. Let's have a look at part 2. What are they asking us? What effect on the equilibrium yield of using a higher temperature? Okay, so when we're talking about temperature, we need to have a look at the delta H that they give us. So if we have a look up here, they've given us a negative delta H. Now, a negative delta H means that the forward reaction is exothermic. And you can have a look back at your fuels and thermochemistry chapter if you're not 100% sure on what that delta H is. So the forward reaction is exothermic. So in our equation, if the forward reaction is exothermic, that means that the reverse is endothermic. Now, the question is, what will happen to the yield of phosgene, so that's our product. What will happen to the yield of that if we were to increase the temperature? Now, we know that according to Le Chatelier, if we increase the temperature, the endothermic is favored. And why is that favored? Well, if we're increasing the heat that the system is under, what's going to happen is the endothermic reaction absorbs that excess heat. Now, in this experiment, or in this equation, that is the reverse reaction. So if the reverse reaction is favored, what's going to happen to our yield of phosgene? So the reverse reaction is actually the reaction that uses up our phosgene. So therefore, if we increase the temperature, the yield of phosgene will decrease. Finally, part 3. Let's have a quick look. So part 3 asks us, what will the effect be on the value of equilibrium constant if we use a charcoal catalyst? Okay, now we know by Le Chatelier's principle, a catalyst has no effect on Kc. But what it does do is it increases the speed in which equilibrium is achieved. Equilibrium is reached. Okay, but it doesn't actually affect equilibrium concentrations. Okay, so that is the third part of that question. Now we're going to have a look at part D, and I might see if I can drag this question down with me so that we can use that for our calculation. Come on. No, it's not moving for me. Okay, so let's do part D. We have it there. Okay, so part D now we're getting into a calculation. So we know when we're doing our equilibrium calculation, we're going to have to set up our little table. So let's rewrite the equation again. We've got CO, the Cl2, COCl2. Now we can tell straight away from that the reaction is 1 to 1 to 1 in terms of its ratio. So actually, we know straight away it's going to be a little bit nicer. Now, what they ask us is, so we've got a 12-litre container, so we know we're going to have to take that into account. We've got 2 moles, 0.2 moles of chlorine and 0.2 moles of carbon monoxide. So they're our reactants, and they're heated at a certain temperature. Calculate the value of the equilibrium constant for the reaction if 85% of the chlorine gas had reacted when equilibrium was reached. Okay, so let's fill in the rows of our table. First of all, so we've got our initial concentration in moles per litre. Again, we're going to track the change so that we can calculate concentration at equilibrium. Okay, now we're told that 0.2 moles of carbon monoxide and 0.2 moles of chlorine are put into a 12-litre container. So we're going to have to divide by 12 to get these concentrations into moles per litre. So that's going to give us 0.0167. 0.0167. So there are our initial concentrations of our reactants. We know as well that our initial concentration of our product is 0. Now we need to calculate the change in our reactants. Now what we're told is that 85% of the chlorine gas had reacted when equilibrium was reached. So what we're going to do is we're going to find 85% of the chlorine concentration. Okay, so that is basically 85% of what we said was 0.0167 moles. So we're just going to take our 0.0167 divided by 100, multiplied by 85, and that's going to give us 0.014195. Now, this is how much of the chlorine gas, and that's in moles, had reacted when equilibrium was reached. So that means that that number is the change in our chlorine. So if that much had reacted, that's the change. That's how much of our chlorine has been converted into product. Okay. Now, because it's a 1-to-1 ratio between our two reactants, if that many moles of the chlorine changes, we have the same change for our carbon monoxide. Similarly, because it's a 1-to-1 ratio between the reactants and the product, if that many moles of the chlorine and the carbon monoxide are used up, we are getting the same number of moles of the product being produced. And now we can calculate our concentrations at equilibrium. So we've got 0.0167 minus that 0.014195, and that's going to give me an answer of 0.0025, and we know that that is moles per liter. So we're going to have the same for here for our second reactant, 0.0025 moles per liter, and we're going to have 0.014195 moles per liter. Now, the question asks us to calculate the Kc, given that 85% of the chlorine was reacted. So let's write out our Kc equation again. Our Kc is our product divided by our reactants, and those square brackets means concentration at equilibrium in terms of moles per liter. So now we've actually calculated those concentrations at equilibrium in moles per liter, so we can just fill them straight into our equation. 0.0025, and that will give me an answer of 2271.2. So that is my Kc. So it was a simple enough equation in terms of the 1-to-1 ratio, but they ask it just in a slightly different way. Instead of telling you the change, they gave you the percentage change. So it's all about being able to understand their phrasing. Now, part E. Le Chatelier's principle predicts best yields in a certain equilibrium process at low temperatures and high pressures. Suggest why these conditions might not be used industrially. Well, we've come across this in our two case studies that we met in this chapter. So they were the Haber process and the contact process. And we know that the reason that we don't use a low temperature, or the reason that low temperature is not ideal, is if we decrease the temperature, it's going to slow down the reaction. And that's actually quite uneconomical. So it's not ideal. Finally, with the high pressure, this is both dangerous in terms of generating that high pressure, and it's expensive. So another reason why we would tend not to use too high a pressure in our industry. Okay, so that brings us to the end of the 2018 question. The next video will bring you through the 2017 question.